in last video we completed hyperparameter tuning. Now let's move towards the final import classification, important classification matrices. So what is classification? We have already seen what is classification in our previous videos. The types of classification we do. Let's move towards the code. I'll import the libraries required. I'll create a dataset, synthetic dataset, and I'll create a synthetic binary classification dataset. I'll create the data frames for better visualization, and then I'll visualize the class distribution here. We can see the class distribution based on healthy and condition data. We will divide our data into training and testing dataset. 30% of the data we will keep for the testing and the rest for the training. We will train with our first classifier, the logistic regression. We'll train our model and then we will make the predictions and we will store the predictions. We'll see the actual and the predicted and the probabilities that are predicted. Once that is done, we will move toward the confusion matrix, that is the foundation of all the metrics. Let's see. Confusion matrix is a table that visualizes the performance of a classification model by comparing predicted labels against the actual labels. We can see TN, FP, FN, TP. These are the four fundamental outcomes. True positive is a correctly predicted positive, true negative is correctly predicted negative, false positive is incorrectly predicted positive, false negative is incorrectly predicted negative. So this is the four cases. Now let's compute the confusion matrix for our data set that we calculated, and this is it. Now let's see it in the form of the proper confusion matrix. Here it's the form of that formula. Now we will visualize the confusion matrix. We'll create a heat map with custom colors and we will add the details annotations. So we have added this FPTP, FN and TN. So this is about it. Now let's move toward the hands-on on analyzing our model's error. We will create a detailed result data frame and then we will classify each prediction into TP, TN, FP, and we can see our classification. And now we will show example outcome by type. So we are just explaining with one of the examples. I will visualize now the probability distribution outcome for probability distribution by actual class and correct predictions versus errors. Both the plots have been plotted here. So this is basics, very simple. All the test cases will give us the total samples. So this is about it. Now we will verify mathematically this relationship. We can see all of our confusion matrix sum up to the total number of data samples, so that is true. We'll see a complete progressive guide now. So we have done till here. Now we will move to accuracy and limitations. So we will recognize what is first we'll see what is accuracy. Accuracy is the proportion of correct predictions out of all the predictions, correct prediction by total prediction. So we will calculate the accuracy of our predicted data set and our confusion matrix that we have created manually. I can first calculate manually from the confusion matrix values, or I can use the scikit-learn. So there are two methods and we can see the accuracy is almost same for both the methods. And when accuracy works well, these are the three cases when accuracy works well: when we have a balanced data set. So let's create a balanced data set with 50% positive, 50% negative, and I'll test the accuracy, and I can see the accuracy is very well here. But let's see what is accuracy paradox. Accuracy paradox is a problem which occurs when model achieves high accuracy but is actually useless or even harmful. This happens when the data sets that we have are imbalanced. So let's see how it happens. So we will demonstrate accuracy paradox here. We'll create a highly imbalanced data set like fraud detection, where 99% legitimate class and 1% is the fraud class. We will give this sample. We have a model A as a dumb model which will always predict the legitimate, whereas B is the smart model that catches 70% of the fault but has the same false positive. So let's move ahead and we will calculate the accuracies and we will see The accuracies is same, but the frauds caught for the dumb model is 0, while smart model caught 70% of the frauds. So this is the paradox. The dumb model has higher accuracy, but it catches 0 fraud. Now let's visualize the accuracy paradox. We can see the fraud percent and then the accuracies, which is misleading, and the fraud detection difference between the dumb model and the smart model. Now, balanced accuracy is a better alternative to avoid this issue. We will import this balanced accuracy score. We will calculate the balanced accuracy for both the models and then we will print it. So we can see the balanced accuracy for dumb model is 50% while it's 84% for the smart model. So balanced accuracy correctly shows what is the picture. Now when to use the accuracy and when to not use accuracy, it is clearly mentioned here. You can go through it. Moving toward the next task, that is precision and recall. Precision is basically measures the accuracy of the positive predictions. True prediction divided by total predicted positives, and this is how we visualize it representatively. So we can calculate manually. Also we can calculate using sklearn, and this is how we calculate it. We have printed it here. What is recall? Recall is, did I find all the positive? That is recall. It measures the ability to find all the positive samples, and this is how we represent it. I'll import the recall score method. I'll calculate it manually as well as I'll calculate it using sklearn, and this is called the recall. Now precision versus recall side by side we will see. We will plot them. This is the plot for precision and recall. Now when to prioritize precision and when to prioritize recall, this is very clearly mentioned here. You can understand it by going through these examples. There is one precision recall trade-off that we have to keep in mind. So let's see how this trade-off works for different thresholds. We have this different thresholds. We are doing passing all the precision and recalls and seeing the predicted positives, and we can see at different threshold the predicted positive are getting decreased, and that is what called the trade-off. Now let's visualize the trade-off. We can see high recall, high precision, and low high recall and low precision, and high precision low recall, where this is the default threshold where everything is around equal. So let's go to specificity now. Specificity is a measure the ability of correctly identifying the negatives. So Tn by Tn plus Fp will give of all the actual negatives, how many did I get correctly identify as negative. So I'll calculate it specifically with manually, and let's see how it is getting calculated. Moving towards the next, we have F1, F2 and F beta score. So let's go one by one. So first I'll go with the F1 score. F1 score is the harmonic mean precision for mean of precision and recall. So let's see what is harmonic mean and how do we do it. So I'll import this F1 score method. I can calculate it manually like this, or else I can calculate it using the sklearn, and then I'll compare them in the output, and I can see it's almost same. Now let's move toward the next is the F beta score family, controlling precision and recall emphasis. So this is the general formula to calculate F beta, and what beta actually shows, this is written here. So first we will import F beta score. We will calculate it manually, F0, F1, F2, and then I'll print it using the sklearn library also, and this is what we can see as the output. Now let's visualize F beta score for different F values, recall, focus, balance, precision, focus. We can see the value differs for all. Let's move toward the MCC, Matthews correlation coefficient. So this is the formula for Matthews correlation coefficient. It is considered as one of the best single matrices for binary classification because of the following reasons written here. So let's first see how we implement it. So I import the MCC, I calculate MCC, I compare the accuracy of imbalanced data, And let's move towards the Cohen Kappa's measure how much better your model is than the random chance. So this is used to measure it, and this is how we used to measure it. We can see the kappa value here, and it says that it's in moderate agreement. So once we are done with this, we are on the part 6, that is ROC curves and AUC. So what is ROC curve? ROC stands for receiver operating characteristics. ROC curve plots the true positive rates against the false positive rates at various classification thresholds. So let's see how do we do it. I import this function. I can calculate it manually and plot it, or else I can plot it using the functions as well. So let's see how we can plot it. This is how we can plot it, and we are seeing the values. Just give me a sec. Now next is the AUC, that is area under the curve. Um we will see the PR curves also, precision recall curves, and here we are plotting ROC curve and precision recall curve, and ROC versus PR curves, when to use, when it is written clear. And let's move towards the multi-class classification matrix. So there are three averaging strategies: micro, macro, and weighted. We'll see all of them. For that, I have imported a multi-class dataset, that is Irish. I'll load the dataset, I'll split the dataset into training and testing dataset, and I'll print whatever I have done till now. Once that is done, I'll compare the averaging strategies with the values, and I can see the guidelines that are defined for this averaging strategies, and when to use which strategy is defined here. Moving towards the imbalanced data set and advanced matrices, the imbalance problem, that is the real world problem. And let's do a comprehensive comparisons on imbalanced data. We'll see earlier imbalanced data, we'll calculate all the matrices on it, and we'll see what the actual accuracy is misleading. Let's see. So we can see here the accuracy is very high, which is misleading, and other matrices reveals the truth. So that's why imbalanced data require a special matrix. MLOps pipeline matrix and best practices we will see here. Now we'll create a comprehensive classification report, and we will create a confusion matrix value. We'll add basic metric, we'll add core metric, we will add probabilistic matrices and generate a report out of it. We'll see the basic practices for choosing the right metric, when to use which metric, and this was all about this matrices. Now let's move forward on classification and regression matrices. Multi-level classification matrices we will see now. We will create a multi-level data set, and then we will generate the values. We will define the genre names, and we will do the predictions on the multi-level data set. There are different categories of multi-level matrices based. One is the example based matrices, other is the label based, and next is the ranking based. We'll see the Hamming loss, that is label level error rates. So Hamming loss measures the fraction of labels that are incorrectly predicted, and let's see how we do it. So first I'll import the multi-level matrices, and then I'll calculate the Hamming loss by Hamming loss function, and I'll print the value, and then I'll manually calculate for the understanding also here. And we can see the manual versus the function, both the values are same, so we have done it correctly. Now next is the subset accuracy. Subset accuracy measures the percentage of the samples where the prediction label set exactly matches. So this is how we calculate the subset accuracy, and we print it. Next is the Jaccard score. So Jaccard score is means like similarity between the predicted and actual label data set, and to calculate it we use the Jaccard score function. We use it for different averaging method like micro, macro samples, all the different methods. And we also do the label based precision recall F1 value calculations. Here is how we do it. And We also do the ranking matrices on multi-level. There are different matrices: LRAP, coverage error, ranking loss. There are different matrices on which we do it. Now we'll do a comprehensive multi-level matrices dashboard, where we will have the example base matrices, level bed matrices, and the per level performance chart, and then we have ranking matrices. So this is the comprehensive multi-level classification report that we have generated on our data. And that's all. We have accomplished all the cheat things in our list. Moving towards the semi-supervised classification matrices. Supervised learning uses small amount of labeled data and combined with large amount of unlabeled data for training. And we will evaluate the challenges in semi-supervised learning. First, let's simulate a semi-supervised scenario. Here I am creating a data set, I am splitting the data, I am doing the second split and printing the splitted data. I'll do the self-training, a semi-supervised method. So here we are doing a self-training because it's a semi-supervised method. Once the self-training is done, we will use the pseudo label for the quality matrices. There are different matrices like pseudo label accuracy, coverage, confidence calibration, label distribution. Here we are using the pseudo label quality. Then after that we are doing per class also, confidence analysis also, and accuracy by confidence bucket. So all this assessment we have done under it, and we can compare the accuracy and the values. Now the next is transductive and inductive evaluation. So in that we will compare the supervised versus semi-supervised performance, and we will do it on unlabeled data transductive, we will do inductive on the test data, and we will do the labeled data sanity check here. And we are printing the values for both semi-supervised, supervised, and we will see the improvement, how it improves. So this is what, and in the next thing we will see the confidence scores, thresholds, and bucketization. So what is confidence score? Confidence score represent how certain classifier is about prediction, and we will explore the classifier confidence scores, and then we will print the analysis. Once that is done, we will see confidence calibration. A classifier is well calibrated when its confidence score matches actual probability of being correct. Perfect calibration is when model says 80% confident and it should be 80% correct. So we'll visualize the calibration curves and we'll see how it actually works. And this is our calibration curve. The dotted line shows the perfectly calibrated, and other are the created by different algorithms. And we can see the quality of different algorithms. Next is the threshold selection for business objective. There are different business goals, there are different optimization, and there are different threshold directions for them. So threshold analysis, how metrics change with the threshold. We will do using logistic regression. We will analyze the different threshold, we will calculate the metrics, and we will plot the matrices based on it. So this is what we are prediction and plotting. Next is the optimal threshold finding method. So these are the different methods which these are best for what and how it works, we have defined here. We have optimal threshold finding method here. We have defined this method here, in which we are doing first is the Udon's J static method, next is the F optimal method, third method is the target precision method, and the fourth method is the target recall method. And then we are doing final optimal threshold for logistic regression, and we are comparing the predictions at different optimal thresholds. And this is what our output looks like. Next thing is the confidence bucketization. The confident bucketization divides the prediction into groups on the air confidence scores. I can see the confidence, we have defined this bucket predictions function. It converts max confidence, and then we define the business driven buckets. We analyze the logistic regression prediction, and then we print our analysis here. And this is our analysis for different buckets and the counts. We will visualize the bucket analysis, we'll plot the accuracy by bucket, we will plot volume by bucket, and then we will plot the confidence versus accuracy graph. So this is what we are seeing here. We can see the prediction volume is low when the number of predictions are greater. For lesser prediction, the it's high. Similarly, it goes for the other graphs. Now, next is the production routing, human in loop systems. So this is the hybrid approach production, when we often route prediction based on the confidence, and this is what we are doing here. And once we are done with this, this is the complete summary. The course has been completed. We have done all this kind of activity. We have defined multi-label, multiple classification, everything we have done. We have seen mean average error and RMSE, and we have also seen R square and adjusted R square here. uh, and this is advanced regression metrics that we have covered. So this is the quick reference and complete metrics cheat sheet of what we have done here in this full course, and the course has been completed for this collab. Thank you so much.